2, test. Test. And
By the way, I didn't find your pointer.
It's okay. I found one. It's not as powerful as yours, but I'll make with what I can do. Thank you for your help.
Nathaniel, I stopped myself from jumping up and go
Yes.
like a cat.
I will ask you to restrain yourself from going forward. Oh, thank you.
Just so you and me think of Fluffy and Peanut.
Yes, exactly.
What are your cats' names?
Tiger and O.
Oh?
Yeah. O.
Like T-A-O-U-X?
No, just O. As in like a James Bond villain character. This is Agent O, or something like that.
Nathaniel, can you talk into the question microphone again, please?
Huh?
Question microphone, please.
Question microphone.
Do I go through A through N?
Yeah. Yeah, that was the end of it. How's it going, David? How's your setup coming?
And.
Is it okay?
Yeah, probably.
Probably better than not. For some reason, Arnie's not on the phone.
I'm planning to steal food when this is over.
That's fine.
You brought the good cookies.
Now, talk.
Hello.
Keep talking.
I want to thank you guys for all coming today. Really appreciate it.
You're welcome. But you can just count.
Okay.
I'm kidding, I'm kidding. I'm not here. I hear a phone ring.
Uh-oh.
That I would be able to explain your paper in one sentence.
One sentence? I
No,
think we'll
just
be
to
able
tell
to
them
do
the
that.
topic of it.
Yes, I think we'll be able to do that.
Maybe the title.
I think I've got a couple of small takeaways that I think everybody should be able to come away with.
Good.
And they're short and quick and easy to remember. Sure. good. Dr. Roy? Hello. I wanted to thank you guys for coming this afternoon to my doctoral dissertation proposal. Today I am going to be presenting some of the work that I've been doing with my advisor, Dr. John Moore, and my title of my proposal is Dynamic Compaction of Copper Mountain Sandstone under both uniaxial and oblique impact with special investigation concerning mesoscale influences. Quite a mouthful. So first I want to do some acknowledgments. I want to thank all of these people. A lot of the people are right here in this room, the Marquette faculty, and all you guys over there and the camera over there. I want to thank you guys as well. The collaboration, you guys have taught me over half of everything I know, so I want to thank you guys. So I have a brief outline here just to go over. I'm going to start off with the background, go into some experimental work, finish it off with some numerical methodology, and then close. So, of course, I'm going to start off with the background. And you can see it's pulsing there. Thank you, Dr. Hugoniot. So I have 3 study goals. I want to characterize my sandstone, figure out what its pore and grain size properties are so that I can do numerics better. I want to do uniaxial wave developments. I want to get the equations of state for my sandstone and compare it with other people's equations of state. And I want to figure out the minimum sample needed to get a adequate sample thickness, because this is a heterogeneous material, and I need a sizable amount of the mesoscale material in order to get a bulk material property. And then finally, I want to do some strength measurements. So let me start off with some types of waves. So if you think about physics and chemistry, you'll recall that most of the stuff around us is either modeled as a particle or a wave. It just depends on the field that you're in and the assumptions that you're making. So I've got 2 different types of waves there that you can make with a slinky. You got these longitudinal waves and you got these transverse waves. So these waves and particles have properties, and these properties move through materials at discrete times and at different boundary conditions, and then they interfere and interact with each other. So as this energy excites local states, you're going to have different sorts of information, sound, speed, travel. So if it's a solid and you're right next to each other, information is going to travel super fast. And if you have a gas, it's going to take a little bit longer for your information to travel back and forth. And then these states change to maximize energy stability. And so of great importance to us are properties of these materials: strength, phase, refractive index, volume, pressure, and temperature. These are the typical ones. And then, so if you understand these properties, you can plug it into more complex models, all the way from quantum physics simulations, the mesoscale stuff, which is what I'm doing, and then you can go super big and just giant lump scale like planets, which is pretty cool. So let me give you a general overview of shock physics. Like all things in life, we're going to start on the simple side. We're going to do one-dimensional shock, no gravity, no change in momentum and energy over a shock, which is a discontinuity in information between 2 states. We're going to call it reversible and adiabatic. We're going to end up with our favorite engineering equations. You see these in dynamics or in fluids, all the same stuff: mass, momentum, and energy. So if we look at our equations, as we want to do, we'll see a number of different variables. And if I look right here, I see 5 variables and 3 equations. 3 equations, 5 unknowns. We can't solve that, so we're going to need a couple closure relationships. So we have an equation of state that we pick out for this temperature relationship between energy and pressure and density. And then we put in a Hugoniot relationship between US and UP, which will give us a PU sort of relationship, or a P rho. Doesn't matter. It just closes all of our relations. And then finally, if you want to get super fancy, we can throw in there as a strength model as an addendum to bridge the gap between solids and fluids. So, solids have plasticity. So if you remember from elementary mechanics, we'll have some sort of stress. And if you look at the simplest relationship, you'll have this Rankine stress, which just involves one of these stress elements. We look at a little bit more complicated, we'll include 2 stress elements. Then you get this other more complicated shape. And then you end up with this circle if you use the von Mises criterion. And you see if you plot it in hydrostatic space, it doesn't change. So no matter what hydrostatic pressure it's initially under, your yield surface is the same. Of course, this isn't necessarily the case. There's lots of materials that are independent of hydrostatic pressure, especially granular materials, brittle materials. And so these have a hydrostatic pressure dependence, meaning that this yield surface isn't the same over any hydrostatic pressure. So what we do is we just put in an extra term, and then we put in a line and a slope. Simple as that. And now we have hydrostatic yield dependence. Pretty awesome. So we start off with this Drucker-Prager model, which you can see right here, and it's just got this extra term inside here. So you've got your J2 stress, same as up here, and then you've just got some of A plus BI. That's a linear line. That's the line of this cone right here. Pretty awesome. And if you want to get even fancier, you can put on this plasticity cap right over here. You can see these are all uncapped. This plasticity cap bridges the gap between pressure shear and then if you have yield under hydrostatic pressure. So this is one of the big takeaways I want you to pull away from here today: strain rate and temperature dependence. Strength of materials is a property that's affected by strain rate and temperature. So if we look at this Instron test, it's just a dog bone sample, and we pull on a sample of material. And if we pull it at different rates, you can see that you get different strengths coming out. If I pull on it slow, I get a lower strength, but if I pull on it faster and faster and faster, my strength goes up. Also, the other thing that you can see is that if I cool off from this blue to the hot red, you can see that we have a decrease in strength. Easy to remember that one, right? Because you have a piece of ice or something like that, you warm it up, all of a sudden it'll go from a solid, which has strength, to a fluid which does not, and it heals. So temperature's strength dependence. And then the other one to easily think about is non-Newtonian fluids. So this guy is doing a same thing of these tests in his hands right here. So you can see as he increases the strain rate that he's applying to the material, it gets harder and it's not yielding. But if he lowers the strain rate, all of a sudden the material yields. And you can think of this as analogous to some of the solids that we'll be thinking about today. How do you measure these strengths? Well, it all comes down to a really simple basic methodology. So you have something that pulls on a piece of material at different rates, and then if you want to get super fancy, and instead of doing it at room temperature, which is okay because that's where most of our interactions take place at room temperature, if you want to be super fancy, then you add a heating element inside there. So these are all the things that we use to measure strength, all the way from creep, which is super slow, tensile testing, all the way over to here to shock loading, and then particle scatter, where we almost can ignore the strength of materials. But the place where I'm going to focus on is right here. But before I go a little bit further, I wanted to draw your attention to this graph right here, just to show you. I really like this plot. It's got the quasi-static strength data, and then you go a little bit higher in strain rate, and you can see what a big difference that does to your strength. So I want to focus on these very high strain rates. I know we have an Instron test machine here, and a lot of other people do, but we are unique in that we have this cool single-stage dual diaphragm gas gun, which has a large bore, which is helpful for myself later, and it has a single channel through it, which is also helpful. But this will allow us to start probing some of these strength-strain rate relationships. Later on, if we exhaust all the stuff that we can do with this gas gun, all you need to do is add a heating element, and then we can apply it for a new grant. Simple as that. Strengthening. So let's look at a couple of the models. We went over Drucker-Prager, so I wanted to go back to this elastically plastic von Mises yield criterion. It's not strain-based. So if we were to plot it, you can see that it's just one value. Not very exciting, is it? But if I use this Drucker-Prager model inside, uniaxial tension and compression, I'm just doing the derivation quick here, and you can see that if you take these terms and then you set the strength and compression and the strength and tension the same, you end up back with the elastically perfectly plastic model. So each of these things will go backwards. But you can see all the things that we did here is we just added a linear, a line element to this. Then we'll make it a little bit more complex. Most of the models today are things like Johnson-Cook, which have higher order terms and include data for different strain rates. So you can see the same element right here in the Drucker-Prager, this linear element, it's right down here. But the only thing that's different now is instead of having that one strain rate Drucker-Prager thing, we've now got a couple scaling terms over here. And you can see one scaling term for temperature and one scaling term for strain rate, just as I was talking about before. And you can see right here we have a much cooler loading path. And this is yield. It's not ultimate breaking, and it's not snapping, it's not fracturing. This is just yielding. So you get plastic stress, plastic flow stress, and it just flows. And it hugs that yield surface. If you want to get a little bit more complicated, you just add on extra terms, and then you have, start fitting these scaling parameters a little bit better, and that's all those other strength models are. So let's say we have this material. First we load it, and we have something under regular elastic deformation. That means that if we push on something and we release the pressure, it'll go back to its original shape. So that's our elastic regime. If we go a little bit further, we'll hit this thing that we in shock called the Hugoniot elastic limit. It's basically the yield strength of the material, but more generalized. So you hit that point right there, and then all of a sudden you have plasticity. You have these different sorts of waves. So you have the elastic wave down here, which you can see just hugs this pressure state. If you go a little bit faster, you get two different types of state. You get the elastic, Hugoniot elastic state, which is a little bit higher because it's under a little bit higher strain rate, and then you get a final pressure state. Eventually, you get to a point where your main wave will overtake your elastic wave, and then you have an overdriven line. And that all has to do with these slopes right here. Once you go past the critical point, you're just ending up with a single wave. So I want you to remember these types of profiles: elastic, these two-wave structure profiles, and then the overdriven one, because we'll come back to that. So in order to probe this space, we typically use these uniaxial experiments. You just impact it, and then the whole goal is to fill up this phase space above the Hugoniot elastic limit. And so this is the phase space for water. And you can see our favorite people right here: pressure, volume, and temperature. What we'll be fundamentally focusing on today is this volume pressure regime. This temperature one, all you do is add in a heating element, and you'd be good to go. So ours is a little bit more complicated than just a regular material. We're compacting porous materials. So I have this awesome simulation put together by Chris Johnson over here and Dr. Borg. It was pretty awesome. And then Chris Larkey animated it. Really cool. And so when you look at different porosity inside materials, you can see that porosity also affects strength. So this is a low porosity, and this is a high porosity, this is a low porosity, and as we decrease in porosity, we increase in strength. You can think of this also, these kind of have two different strengths associated with them if you really think about it. So imagine a spring as a porous element, and instead of compaction, we're going to do tension. So you have the spring, it's got the elastic regime, right? You pull on it, it might have some sort of a plasticity, right? And you'll be getting the properties of the spring. But eventually, if you pull on it, pull on it, pull on it, you'll no longer have a spring, you'll have a solid metal rod. And so then you'll go from the material properties of a spring, a mesoscale property, to a solid property, which is just the property of the steel that you're pulling on. So you have to keep that in mind when you're working with these materials. So you have this porous curve, and eventually it'll fall onto this solid curve. Quick overview of pressure shear. Why do we want to do it? So typical uniaxial experiments will just load us in one principal stress area, but pressure shear takes us off that axis and gives us a little bit better of a yield surface, if you remember the Drucker-Prager. In order to do these, we use the oblique impact experiment. It has a number of uses: dynamic friction, viscosity of materials, but we're going to use it for pressure shear experiments. So of interest in this study is the distortional strength model of sandstone. So you can see this data that already exists. This is at low strain rate. So we would anticipate that we might have a larger curve right here when we go at higher strain rate. But if we look at porosity, you can definitely see that porosity is having an effect on strength. I've normalized it here, so if I actually were to take off the non-dimensionalization, you can see that the sandstone goes and has that same curve as we saw in the previous slide, where it's getting much stronger for lower porosity. The specific test that I want to do is pressure shear, and what we're going to do is we're going to take a flyer and we're going to impact another material. So we have our system right here. We've got a sabot and a piece of metal on the front, and then we're going to impact the material at an angle. And based on the wave structure, we're going to first load it in pressure, then in shear, and then we're going to get our yield surface. It's really difficult to do it one way. If we tried to load it in shear first, because the shear wave is always slower than the longitudinal wave. So you first got to load it longitudinally, then in shear. So that's how we're going to get there onto our yield surface and populate our curve. So why are these porous earth materials worth studying? Why do I want to do SiO2? Because if I look at the composition of bulk earth, look, Si and O2, big pieces of the pie. I look at the oxide composition of the Earth, look at my number one oxide in Earth, it's SiO2. Think about it, in granite, you go to the bottom of the ocean, what's there? There's sand, SiO2. It also has similar concentrations in other planetary bodies around our solar system and elsewhere inside the universe. So it's a pretty interesting material and it's worth studying. The other reason it's worth studying is because it's found in many different stable forms, all the way from this really low porosity aerogel, all the way to this really high density crystalline quartz. Now, if you look at the shock behaviors and then the pressure shear materials, there's been some studies done in the past. I've seen pressure shear results done for crystalline materials, as well as recently here at Marquette University for sanded pressure shear and high strain rate. So, I would like to put my stamp right here. If you notice, the casual observer will note that there are 2 extra slots that are currently available for enterprising undergraduate, graduate students. Study applications. So granular materials and porosities are of great interest to people, especially with other people who have porous materials, whether those be brake pads or something like that. Propagation of force through these geometries, these force chains, that's pretty interesting behaviors. And it's really important for knowing structures and foundations. You can see in the scientific community, that's what we use to do simulations and what we use to understand the materials around us. Other applications, we've got momentum enhancement. We have mining and fracking, so that's made out of SiO2. That's how you pull out the oils. Structures engineering, and then finally asteroid impact. But as I said again, you can also have stuff like brake pads. It's applicable to a wide range of applications. Next, I'm going to go on to my experimental work. How am I going to do this? So I'm going to go 3 different things. I'm going to do grain property characterization, characterize my grains. I'm going to do a couple of uniaxial shots, figure out my properties of uniaxial sandstone. Then I'm going to try and do strength studies with pressure shear. So I initially looked at 2 different types of sandstone. I had this loosely consolidated sandstone, which was really hard to work with. It hadn't really undergone diagenesis and it falls straight apart. And then I have this well-consolidated stuff, which is much closer together, so I can machine it, which is awesome. To prepare it, I drilled it out, then I lapped and cut it, and then finally I could machine properties into the sandstone. This average grain size allowed me to cut samples as thin as 0.5 millimeters, which was interesting because my largest grain size was 500 micrometers. I think there might be a correlation there. In order to characterize the actual grain properties there, I looked at some 3-dimensional characterization techniques, but then eventually I went to 2-dimensional characterization. So I had this virgin material after I cut and lapped it, and then I was able to use a 1% buffered oxide solution etchant, and then you can see that I'm gradually whittling away my boundary areas. Eventually it becomes really porous, so I'd recommend etching somewhere between 60 to 120 minutes in order to get your characteristic grain sizes and stuff like that. Once I have my etched sandstone, I put it in through a linear image registration with MATLAB, combined all my pictures together, did some erosion, boundary identification, merged the data together, did an edge discard, and then found my grain size distribution. I could use ImageJ, and then I got some sample statistics out for all of my grains. I think I had a total count of 5,214 grains after I did the discard. That was to make sure that I didn't have any boundary grains or ones that were too small. In order to get the 3D grains distribution, I used the Saltykov method, thanks to Dr. Furnell, which takes 2D spheres, makes them into 3D spheres. There was an awesome processor, I verified it, for the Saltykov method that I was able to take my distribution into, and I got a good distribution for what my 3D distribution was. And then I fit those 2 distributions using a maximum likelihood estimation. You can see these are bimodal. So here's a summary of my properties. I've got a solid density of about 2.6. It comes to about somewhere between 7 and 14% porous at the high end, and on the low end I get about 6 to 4. And these are just averages of all those numbers. Spectral imaging, I was able to put this into our spectral imager. As you can see, it's mostly SiO2, which is a good sign. And then I put it into a X-ray data comparator, and I was able to see that our grains that we mostly had were probably alpha quartz. You can see we've got a lot of peaks that match up really well inside there. So with these, I can build models later on. So I have 2 initial target designs, and I'm going to shoot them in our Mark III single-stage gas gun. We have this single uniaxial sandstone target. We just hit the face, and then the other target that we have is a 3 sample, so we can monitor the effect that grain sample thickness has, and figure out what the minimum thickness that we can use for a heterogeneous sample is.
Dan,
Yeah.
Can you just go back and slow down on that slide? So you got this piston, right?
Yeah, it's pretty much a piston.
Right, okay. And where's the sandstone? There's a thin layer. Where is the sandstone?
So inside the large uniaxial target, it's just sitting at the end of the barrel right here, and then we impact it. And it's just...
Well, how thin or thick is the sandstone?
I've gone from 0.5 micrometers all the way up to, I think it's 6 micrometers in thickness.
That's like really thin.
Millimeters.
Oh.
0.5 millimeters to 6 millimeters, sorry.
Oh, like a quarter.
Like a quarter inch or so.
And so basically, you're ramming this thing in, right? And
Yeah.
You're hitting it.
Yep.
And then you're measuring. What are you measuring in the sandstone?
I'm measuring the velocities that are coming out the back. So you can see as the waves travel through the material, you get 2 different things. You get the pressure that's coming out, a UP, a particle velocity, and then you also get out a time that it takes for the wave to travel through the medium. And those will give you enough information to populate a pressure specific density regime. And that will be used for an equation of state.
Okay, so in other words, what you're trying to do is to describe basically the material properties of this under really high strain rates.
Exactly. So it's an instron test, but really fast.
It's a fast instrument.
It's a fast instron. Yep. One of the fastest out
And
there.
when you do this, does this make a lot of noise or something?
No, actually it doesn't. It fires into a vacuum. So it doesn't, it hardly makes a pop. You can feel it though, but you can't hear it. After the gun is finished firing, the system is still under vacuum.
Well, I remember 10 years ago when Dr. Pore was shooting something over there and it
Baseballs.
was really loud.
I don't think you had a vacuum back then.
Yeah, but that gun didn't have a vacuum.
And because we had an adjacent lab and we had to clear out. because-
Well, we still clear out the labs just in case.
Okay, all right, okay, now that's all right, okay.
It's just a big strain rate tester. And if we wanted to make it more complicated, you just throw in temperature measurements, and then you can populate the PV-T space. But right now we're just focusing on PV. It's hard enough. Hey, that's more work for other people later. I like it. We see where it's going. Finally, I want to look at my numerical methodology. After I've done my experimental work, I'd really love to make some models, and the way to test your model is to put them inside of a device or a numerical method. So that's what I'm going to try and do. So the computational tools I'm using, CTH, it's an Euler layering Lagrangian massively parallel code. It's great for, it was typically built for hydrocode, so that means everything's hydrodynamic, but then they added strength models, so it's technically valid for elastic impacts as well. So it can model a wide range of different types of experiments. Dream 3D, this is what I use to make my mesostructure. It comes out of the ARL, synthetic microstructure reconstruction. ImageJ, that's what I use to post-process my different grains. And MATLAB, this is what I use to use my data processing. Finally, to do visualization, I use this program called ParaView out of San Diego National Laboratories. And then to do a little bit more of my elastic wave studies, I've played around a little bit with Paradigm. I may put it as an addendum inside of my doctoral dissertation, rather than a full part though. So I started off with this P-alpha simulation, and a P-alpha model just assumes that some sort of heterogeneous material has porosity properties. So it's not great, but it's a good first guess. And so I had this 2D rectilinear domain. I put in some equations of state. You can see I used the alpha quartz model based on what I have, iron and PMMA, because those are the materials that I'm using to hold it. And then I have the strength models. For the sandstone, I used an EPPVM model that I got off of I think it was either Gregson or Aarons and Johnson. And I went back from a Hugoniot elastic limit to find the yield strength. And that's valid because they did the test at high strain rate. So here's the initial conditions. We had an initial velocity of 100 meters a second. And you can see this wave come through the first material into this material, go through the sandstone, and then it hits the back wall, and that's where we collect our data. And so based on how the data goes through this sample, that's how we collect it. So let's see if I can do it one more time. So you can see the material go through, and the impact goes through the sample, and you can see the wave change around here. That's the elastic portion. This is the plastic portion. And then it hits the back surface, and that's what we record off of the back. Here I've done a number of different simulations. If you recall from before, I'm going to do a callback. If we look at this one right down here at 100 meters a second, you can see it's got one wave, and it's really slow velocity. But if we look at this higher velocity one, this at 200 meters a second, we can see that we've gone above the plastic regime because we've got two waves. We've got this small one and then a bigger one, right? And then you can see that slowly starting to taper off in this 400 meters a second one. And by 500 meters a second, we've overdriven our sample. So you can see that from before on our different slides. So then I started to do some uniaxial thicknesses, uniaxial simulations that were a little bit better. So I built this 3D model in Dream 3D based off of the grain size characteristics from before. And then I sampled those, put in some equations of state, given some strength models based on quartz this time, since I'm giving the strength model to the grains rather than the whole body as a whole. And then I give it some initial conditions, and you can see right here, I have this impactor, and you now get compression of the grains as you go through and decreasing porosity, which is pretty awesome. And so let's go and compare it. This is a pretty busy plot, but I draw your attention to this one over here. So this stuff in dotted lines, these are the P alpha models. So that's the pretty approximation for a homogeneous, heterogeneous material. You can see right here with my new stuff, this solid line right here. These are my simulations with mesoscale features. So, and then you can see right here, these light lines right here. These are some experiments that I've run. I still have some more to go though. But you can see that my mesoscale stuff is fitting a little bit better than my P alpha model, which is pretty cool. Then I want to do some pressure shear simulations. So once I finish with my uniaxial sims, I want to do pressure shear to get strength. So before I was getting equation of state, now I'm getting strengths. And in order to do this, I have a material in the front and a material in the back. And first I load it under pressure. And you can see that I've got two different pressures on the front and back surface, but eventually they converge together. And after they've converged together, then I put in a shear wave through those materials. In order to do this, it's really important that you have anvils that are about the same impedance as your other material. That just means that the information traveling in one is close to the information speed rate traveling in the other. And that decreases the number of rings that it takes to get a steady state longitudinal pressure. So you want to be up here before you put in the shear. Otherwise you won't be at full hydrostatic compression. So when we go to our Drucker-Prager model that looks like this, we want to go hydrostatic, then distortional. So that's how we're doing it right there. And you can see on this back surface we have the hydrostatic, we come to a steady state, and then we can measure this shear coming off of the back. So theoretically we could hit the sample with an identical impedance and then we would get immediate pressure state, but we need something that's a higher strength than the material we want to study. Because if our anvils yield, then we're measuring the yield of the anvils and the material, and it's really hard to parse them apart. So you want anvils that are higher strength than the samples that we're trying to measure. So it gives us a whole bunch of constraints for our experiments. And you can see right here I'm trying to do different timings to make sure that my longitudinal waves fully brings up my sample in 3 waves, 1, 2, 3, which is about 95, 96%, before this shear wave arrives right here. And then this is my timing window where I'm allowed to measure each of these different states. So between here and here I measure the pressure state of 1. Anyway, just a bunch of optimization there. So here I have a simulation. Here you can see the longitudinal wave, this blue wave coming into the sample, and then following right behind it is the shear wave. The shear wave goes through the sample next, and then you get the pressure wave coming off of the front, and you get the data, and then the shear wave comes off the back, and then you get the shear data. And so that's how you've measured the strength of material under pressure and shear. And you do that at a bunch of velocities, you get a bunch of different hydrostatic pressures, and then you can get different distortional pressures. Finally, I have some closing remarks, hypotheses, and conclusions. So I hypotheses through this characterization that if I increase the amount of information that I put into my numerical models, the increase of information that more accurately models the actual stuff I have, the closer I will get to what I really have. So I want my numerics to match up with my sims, and the more information I put in, the better that comparison will be. Basic I think that one's a pretty good hypothesis. Uniaxial tests. I want the heterogeneity of the sandstone samples, especially at low thicknesses. This is important because I'm trying to measure the strength of sandstone, not the strength of quartz or the strength of the pores. So I need to make sure that I have a maximum thickness of sandstone possible while still being able to do my pressure shear experiments. Because if they go too thick, I won't be able to load it up in pressure, then in shear. I won't make it. And then finally, a sandstone material having higher microscale density will have a higher bulk material strength and not a less porous media. So we'll see if that's the case as well. If I can do enough pre-characterization, maybe I can see that there's a porosity-strength relationship. But it'll be a lot easier to do than something like sand, where it's harder to control your porosity. At least I can pre-characterize to some extent. Finally, I want to do these pressure shear tests. So I'm thinking that sandstone should have a higher bulk material strength when compared to previous data collected for sand. So this is this high strain rate data for sand. And if I do my tests, I'm hoping that my sandstone curve will fall above the yield surface for the sand. So I'm hoping, as from before, remember when we had the sand and the sandstone at low strain rate, I'm hoping now at higher strain rate, we get the same behavior, just at higher strengths than low strain rate. I wanted to thank you guys for coming to my talk. If you've got any questions, we have a question microphone over here so that the folks at home can see you. If you guys have any questions, please don't hesitate to ask. Thanks.
I have another comment. Why am I the only person talking? Because everybody else knows what he's talking about. Should I go over there?
Yes, please. The chords.
My name is Richard Marklin, and I'm a professor in mechanical engineering, and I'm certainly not a materials person or a shockwave person. I think you've done a really good job taking something really complicated and explaining it with a lot of good graphics, and so I think I'm starting to understand what you're really doing. And you mentioned some of the applications of this, but I just want to tell you about another application that that I learned about just a few months ago. In the last 3.5 months, I was in the Netherlands. And the Netherlands has a really well integrated public transportation system. They actually have 5 modes: trains, trams, et cetera, even going down to water ferries. And even for a relatively small size of city, their train station, they spend up to $1 billion on one train station. And that's connected with the buses and everything. And so in Delft, where I was, they spent $750 million on this train station. And during the test phase, what they found out is, and this relates to pressure waves, when the trains came in through the tunnels, the pressure wave was so great, it blew out some of the windows on the first floor. Now, fortunately, there were no people in there at the time. So what I'm saying, Nathaniel, is I think all of the theory that you have right here could be applied to that, right? Right? I mean,
Strength of materials, fluids.
Everything. I mean, it's a
Yeah.
pressure wave, right?
Yeah.
Having the subway coming in really fast. Do statistical hypothesis testing
Yes.
using
definitely.
analysis of variance.
Especially because I really want to know that the model that comes out of my numerically grown sandstone matches up with my initial experimental data that I had going into it. So when I pulled out those 2 bimodal distributions, I want to be able to compare that with my original.
So you're going to be comparing the means and testing whether there's a
Yes.
significant difference with the P level, and then you said you are also going to test you're going to make sure the sample size is great enough so you have at least 80% statistical power.
Exactly.
Wonderful.
The
Nice.
little trick on that one is I have log normal distributions, so I got to do a conversion over to normal
Okay.
distributions.
All right. That's all. Thank you.
Sounds good.
So if we want to ask a question, we have to go over there?
I can also field questions from over here and then repeat it.
Oh,
Okay,
okay, well, I got two questions.
2 questions.
One, how does sandstone yield? I mean, you've got a model in terms of grains of different sizes, mesoscale things. How is the yield, how's it gonna yield? What's the mechanism?
So sandstone as a overall bulk material, its yield is going to be pretty interesting. If you have just a bulk material, you're going to have movement of atomic structures, and you're going to have voids within inside of your material, and those are going to move over each other, and then you're going to have flow stress inside of your material. But in sandstone, it's really interesting because you have those pores. Not only do you have all those mechanisms of strength that you would have in a crystalline material, you also get pressure hotspots because you have sharp corners, and so you'll have some regions which will liquefy immediately, and you'll have jetting within inside of your sample, which is pretty interesting. So you have to include those inside of your strength models and in your simulations if you want to capture the full failure of sandstone as a mesomaterial rather than just a single crystalline grain.
Okay, then there's my second question. If you have these phenomena going on between the grains, i.e. the melting, etc., how are you going to characterize these changes?
So while I can't do anything in situ, there are some places which can do XCT at a phenomenal rate, but I don't have access to those at the moment. What I'm going to do is, if I might try some additions, if I have time, I'd probably like to do some post-mortem observations, as you can see right here. So inside, I'll probably be able to see, so in this post-mortem analysis, I saw some still chunks of fully consolidated sandstone material, so maybe parts of it were elastic. It's hard to tell because so much else happened after these, but maybe this sample was loaded elastically. And hopefully, if there's something like jetting or grain crushing, I might be able to see a difference in grain sizes after my experiment's over. It's not a perfect method by any means, but at least it gives me something to look at before and after. So you start off with one of these, and then maybe you can look inside the cups and see what you're left with. These are recoverable, so I can look at it after.
So is this stuff primarily crystalline, or is it all amorphous?
It looks like it's primarily crystalline based on the X-ray powder melography that I was doing before. If you looked at those different peaks, the peaks that were there were indicative of crystalline behavior. If you look on the far left of it, let me try and get back to that slide. Back. Excuse me. Oh, there it is. So if you look at these different peaks right here, these are crystalline peaks. There is a small slight hump over here, and that could be a little bit of amorphous silica, but the vast majority of the signals that I was getting off were definitely crystalline peaks. And then comparing with other crystalline materials, the one that it matched up best with was alpha quartz. You bring up another good point though. Since I'm doing this post-mortem stuff, I could take some of my post-mortem samples, grind them up really fine, throw them inside of the X-ray, and see if I get different phases afterwards. That would be pretty cool to see if I got changes in crystalline type. If I went from something like alpha quartz to beta quartz, or maybe even some stishovite, that would be pretty awesome. David, you have a question.
Yes, this question is from Arnie. Nathaniel, how did you pick your PS in your P alpha model? It's set to 1E9. Just curious if you have a sense of what range of values might be appropriate.
Can you repeat that again a little bit slower, David?
How did you pick your PS in your P alpha model? It's set to 1E9. Just curious if you have a sense of what range of values might be appropriate.
Okay, so if I go forward to show what he's talking about. So I'm just starting my initial uniaxial and P alpha simulations, and I'm kind of hoping to do a different range of different PS values, just to see what effect it has. I just started off with this one. It's still just in the beginning phases, and I probably need a little bit more fine tuning on my P alpha model. So I will definitely work on doing some more different numerical models to try and fit my data better. This was just a first pass proposal.
Fair enough. Trick question.
Thanks, Arnie. Dr. Ernest.
What happens to temperature during shock loading?
What happens to temperature during shock loading? Typically, the temperature will go up, and then when it releases, the temperature will be a little bit higher than after the wave went over it, before the wave went over it.
Goes up.
So let's say you have something like copper, and you shock it up to 1 megabar. That would go up to, I'm going to guess, a couple, something like 700 Kelvin. I'm spitballing here, but this is all orders of magnitude. And then when it falls back down, if you were something at like 300 Kelvin, it'll go up to something like 320 Kelvin. And these are all like very broad estimate numbers, but I can get back to, I have a really cool program. There's a really cool equation in Jerry Forbes' book on shock waves, and he's got this really awesome equation that'll take you up in temperature and then back down when it's released adiabatically. But because of that chaos, a little bit of that temperature is left over inside of the material. It doesn't go back down to its original temperature after the shock's passed.
But if it happens so fast, you don't expect any transformations due to temperature?
I do expect some transformations due to temperature. So if I go back to this plot right here on the strength plot, I should have pointed this out before, but I had a couple extra curves inside of my PV diagram. Let me pull that out. Sandstone, it's going to be in the literature review section and initial work. Further back, there, right here. So when we go through a different type of material, we have all these different types of curves. So initially, when people started doing shock physics, they assumed everything was isothermal. And so that's what this cold curve is right here. Cold curve, isothermal. But that didn't quite match up with data. Then they tried this other one, which was isentropic. It was a little bit better, but finally they came up with this Hugoniot state, which I think is, correct me if I'm wrong, Dr. Borg, it's really close to adiabatic. But it's just a locus of different states that it reaches from an empirical standpoint. This is all empirical work. It doesn't quite match up with cold curve or isentrope, so it's not isothermal. But it's interesting. These are good, they're okay approximations, especially at lower temperatures, at lower amounts, but as you get bigger and bigger and bigger, your discrepancy increases by a whole bunch. Dr. Moore?
I had a question. You talked about the effects of porosity and wanting to characterize those. Is there an interest in putting those into a model? And if so, what model, what's the approach? What approach would you take?
So there, at this point, if I was to start off, I've only got 2, maybe 3 set points. The other thing that's a problem, like I've got 3 different types of materials. Maybe at the end of this study, I'll have 3 different materials. I will have the sandstone, I'll have sand, and I'll have maybe some crystalline data. The problem is when I go from sand to sandstone, my grains aren't necessarily the same. So if I was to make a model for sand to sandstone to crystalline material, I would call it natural, like natural porosity. Because if you look at the porosity of sand and sandstone in the triaxial test, you would notice that even though I normalized and there were slight differences in porosity of the sandstone still had a higher yield strength than the sand did. I'm not quite sure where it is. I gotta escape. Oh, computer's chugging a little bit. But it would have to be something like porosity of naturally occurring silica forms.
Okay. So does your CTH simulation have porosity in it?
CTH has porosity in the uniaxial model because I put it there. I put voids and I put solids. And then in the P alpha model, it just gives a slightly different yield value for, okay, we're going to have some compression, and then we're going to allow for a fully dense wave to go through it. And that's why all the waves are so clean and they look so idealized.
Okay.
It's because they are idealizations. Ideally, what I try and do is I try and make an empirical model based off of my results, and then try and feed that into CTH for a different sort of P alpha strength model.
Okay.
Maybe not include porosity. I don't know. I'll see what data I have and what things I can fit. As long as I've got 2 data points, I can make a line. Whether or not we should make a line, that's where you get paid the big bucks. Yeah, in this model right over here. So here I've normalized, and you have all these different sample porosities, and you can see all the sandstone data falls onto itself. But this sand, which has, I think it may be a similar type porosity to one of these other ones. Actually, it's a similar type of porosity. When you non-dimensionalize it, it still has different behavior than your sandstone. I think it's probably because of the grain shapes. If you look at the sandstone, it's undergone diagenesis and everything's kind of cohesed together. You get all those little sharp points.
Okay.
Thanks, David.
Well, it's bonding, right? It's like interparticle.
Yeah, and whereas you have the grains, they're round. A lot of them are round, but some of them can be jagged, and all those different shape factors mess around a lot with your data. I think. Yeah, when I went to SCCM this year, there were whole talks on just different types of shapes of grains and how that would affect your strengths. It's a big problem. I got to tackle a small part.
Is there anything in the sandstone besides SiO2?
A large portion of it was SiO2. If there's anything else in there, I would guess that there's a little bit of aluminum oxide left in there from the lapping process, and then there may be trace elements of other materials like feldspar. But the majority of the atomics that I was able to pull out of my spectrogram, it looked like the majority of my elements were SiO2. I think I zoomed in a little close on it, but there aren't too many other peaks. So let me just pull this back up again. So you can see right here, looking at my elements. Oh, click, click, click. Looking at my elements, you can see little trace peaks of other things down inside here, but the vast majority of the material is SiO2. And this is zoomed out. So I zoomed out and I took a broad picture of a number of grains. But I would guiltily say that there may be some trace flecks of aluminum oxide. I try and take that out through like cleaning. You've got that pulsar, a hydrosonic pulsar for cleaning jewelry and other types of materials, and I try and soak my samples afterwards to try and leach out as much of the aluminum oxide as possible before I shoot. Dr. Erdness.
Those porosity levels that you have, why is it so different? Is it sample-to-sample radiation? Is it the testing method?
Yeah, so one of these, this one that came from Central Wisconsin Stone was a rip sheet. And then the ones from Lab QMC were taken from our specific, one specific cut of our material. And I try and get initial density values by doing some dry weighing and size characterization. So if I know the weight of fused quartz, and then I know the volume of my puck, I can pull out a rough porosity.
What do you mean by strength?
Strength?
Yeah.
This is probably tensile strength, to be honest. Bulk tensile strength.
UPS?
Yeah. I didn't say, it just said strength on the rip sheet. So I left the other two blank over here, but I just wanted to put it out there. And then these are the chemical properties that came off the rip sheet as well. And so from Central Wisconsin Stone, they said that I had 98.94% SiO2, and then some trace elements of iron, aluminum, potassium, some of these other materials, but mostly silicon dioxide. And then looking over here, I would guess that most of it is alpha quartz based on my peaks. If you have better methods for quantification, or I'm missing an obvious one, now's the time. I've got a little while to go. Dr. Pore.
With regard to the experiments, what are you proposing to do exactly?
Okay, so with regard to the experiments, I'm proposing to do two different things. So I want to characterize the samples. I want, for uniaxial, I want to do a number of extra tests for different sample thicknesses to characterize wave propagation, as well as characterize final states that the sandstone gets to. So that'll give me one of my constitutive relations.
Which one? What are you going after here?
So let's say that I have these 5 equations: mass, momentum, and energy. Where's that one? Right here. But I would like, ideally, if I can do it, is I already know mass, momentum, and energy, but I would like to know these 2 closure relations for my sandstone. I want to know my US-UP relationship. I don't know that I'll be able to pull out an equation of state, so I'll have to use that from somebody else. I would like to pull out this Hugoniot relationship for my sandstone, and I would like to pull out a strength model for my sandstone.
So
Those 2
you
items.
showed those strengths up there that are measured, so how's what you're proposing to do different from what's
So
been done?
if you've been thinking about these, if you're referring to this graph right here, this one, I think is the one you're referring to.
Sure.
So this is at normalized triaxial tests. And so this is at low strain rate. And so the reason why my study is important, the reason that Jeff's study was important, is we're doing it at a different strain rate. If you recall one of the diagrams that I had in the upper right-hand corner, you could see that strain rate had a large effect on strength. So the way you figure that out is to measure it empirically. The other thing that you can pull out through these pressure shear tests is you get these caps. And you get this pressure distortional stress. If I just was to pull on it in uniaxial, I would just pull out these values down here, which wouldn't be as cool as mapping out an entire hydrostatic distortional stress regime.
So how many experiments are you proposing to do?
I'm proposing to do about 10 uniaxial and 10 pressure shear. If I've got time, maybe more.
How much time are you going to need to do 10 and 10?
Probably a year. I've got a number of uniaxial experiments ready to go over this break, if the proposal is accepted. Otherwise, I might have to go back to the drawing board. And then you can see that I've got some of my pressure shear materials, and then designed for an anvil all put together. So we'll see. I'll have to go to the machine shop and see what I can do.
How are you proposing to make your measurements?
Using velocity probes. So I'm measuring off the back surface the different types of waves that come through the material. So I measure the waves, the amount of time that it takes the wave to travel from the front anvil to the rear anvil. That'll give me US. And then if I measure off of the rear surface, then I'll get my UP value. And for pressure shear, I'll need at least 2 probes, one to measure in the normal direction and then one to measure in the shear direction.
Do you have like because in the proposal that you sent out, it wasn't necessarily like a test matrix of what you're listed.
Oh, okay.
Do you have such a beast?
Not on me, but I do have it. It's on the upper right-hand corner of my cubicle.
Yeah, it'd be nice just to say, you know.
Yeah. So I want, in the numerical matrix, the first thing that I'm testing while I don't have my experimental data is I'm just testing mainly what yield strength has as an effect on the sandstone grains. So there isn't really great data out there for what the yield strength is for quartz crystals. And so I'm just doing a number of different yield strengths for the sandstone quartz crystals in order to see what matches best with my uniaxial sims. And then once I have my uniaxial sims, I'll be able to pipe that into my pressure shear and see if it works.
What do you think is going to be more interesting, the simulations or the experiments?
I hope both are equally interesting and they cooperate each other.
Which do you think was the more unique contribution to the field?
The experiments, because those are harder to do. Not anybody can get a hold of CTH and do these numerical codes. I happen to be blessed in that area, but even rarer than being able to get a hold of a numerical code, I suppose I could get a hold of ISAIL or KO and try to do some of these, at least for uniaxial. But the experimental work, the lead time in trying to learn how to prepare sandstone samples is quite a bit, and it takes, I think, it takes a little bit of craftsmanship at this point. And I don't think there are going to be other people that are going to be super excited to go out and do that. It's quite an investment.
No one shot sandstone?
There have been shots in sandstone, but those are uniaxial shots. This is pressure shear. I couldn't find any pressure shear sandstone shots. I think for most people, they've looked at sandstone and they've said, well, this is pretty, well, A, pressure shear is relatively new in the shock field. But B, in order to try and get pressure shear on a heterogeneous material, that's pretty different. That's pretty difficult. I think one of the first heterogeneous samples I've seen was here at Marquette in my reviews of shock. I think the first one I was exposed to was Jeff, who did a mesoscale. There may have been some more at SCCM and stuff, but I think that's pretty unique. A lot of people just do really thin samples in pressure shear and of very homogeneous materials.
Is there a design for your experiment?
Which one?
Like the pressure shear one? Do you have a design?
Yeah. So this is hot off the press, so this is a little early. But you could see my first design right over here for some of my pressure shear. So I have two anvils. They're about 0.8 centimeters thick. And so you can see my XD diagram right over here. I get just enough reverberations to get to my steady state, in my opinion, or as close as I'm going to be able to get through my 6-thick sample.
What is that material?
This is sandstone, and then these two materials here are aluminum 7075 T6.
Okay.
I tried looking at other materials such as Chris's steel, but its impedance is really different. So when I plugged in these front and rear anvil state trackers, if you use something that has a higher strength, but off impedance, it'll take so many rings to get up to the full steady state that it's going to take too long. If somebody was willing, and somebody had the resources, I'd really love it if somebody could give me some machine plates of tungsten carbide or maybe sapphire. Sapphire would be pretty good. But you also got to be able to machine it to put in the pins and stuff like that.
Why do you need that stuff?
It'd be closer impedance and higher strength. Tungsten carbide, higher strength, which means I can do more in my shear stress distort.
What size sapphire? Sapphire discs?
Sapphire discs.
What size?
Probably 2 inches in diameter, but they also have to be machinable.
Why?
I need to be able to put pins and probes around the surfaces of things and measure through the samples, because I'm coming right up against the limit of what I can do for my sandstone diameter. If I had access to something like a 4-inch gas gun, I might be able to slightly increase the size of my sample a little bit more. But right now, 2.1 centimeters seems to be my limit, which ironically seems to be the point at which my uniaxial homogeneous samples seem to be converging to right about 1.8 centimeters. So it's tight, but I think it's doable.
That says something physically, like the fact that you can only, that's the physical limit you can make it, and it's the physical limit where it converges?
If you think about it, each of the nominal grain size diameter is about 100 micrometers. And so if I have a sample that's 2 centimeters thick, and the biggest grain size is 500 micrometers, so that would give me, in my thinnest samples that I was looking at, 1, so that would give me 2 full size grains in there. But if you go up to 2, that gives me full 4 size grains, and quite a bit of those nominal diameter, I think that was 120 micrometer grain sizes. And that gets me closer to my homogeneity for a heterogeneous material. It sort of makes sense when I've talked to Dr. Borg in the past and asked how many spheres do I need or something for something like those sugar grain calculations. He says maybe something close to, what was it, 10 to 13, Dr. Borg, you recommended? So I would be curious. I got to do the math really quick and see how many 120 micrometers fit in the tube, but it might be getting kind of close to that ratio.
Sure.
Do you have any suggestions, any resources? I think I'll look into talking with Mr. Silman about Sapphire, maybe. Thank you. Well, help put yourself to some stuff as you go out. We've got plenty. Hey, Ernie. Did you have any other questions?